We'll start. John Bird, well, tell us about wave theory.
Great. Thanks, Daniel. So can everybody see the whiteboard, hopefully? Why they happen? To diagram out the parts of a wave system so you can recognize sort of these parts and where they occur, which will help lead into Phil's talk about how, and Daniel's talk about how to exploit wave and where to find it. And to try to help understand why some waves go high and some don't. Right? There's wave soaring days that some of them you can climb a diamond altitude, and some days you climb up a little ways and then you kind of get stuck, it drops off, and you're not getting any higher. So that's going to be our primary goal, and if we have a little bit of time, we might talk about some weird things that can happen in wave at the end. But we're going to start to figure out what a wave is, and in order to do that, we're going to have to go back a little bit and understand a little bit about atmospheric structure. So we're going to look at the vertical profile of the atmosphere. So we're looking at altitude on the vertical axis and temperature across. Right? So if you're familiar with the SKU-T plot, this will look pretty familiar. We have the temperature decreasing with height for quite a while, pretty aggressively, and then it may warm up or just stop decreasing for a while, and then it's going to start cooling off, but much more gradually. Okay? And so this is the boundary layer. This is where we do all of our thermal soaring. In the winter, when we're looking for wave, and in general, it's going to be somewhat thinner. And then this is the inversion, which caps the boundary layer, and then we're up into the free troposphere, the rest of the lower layer of the atmosphere. And so when we're going to introduce the concept of stability here, where we have a piece of air. You imagine kind of an imaginary balloon full of air, right? We could draw an imaginary line around this and say, here is an imaginary balloon. We're going to call it a parcel because meteorologists like the term parcel when we talk about bits of air. And the question is, if we displace this bit of air up or down, what is going to happen to it? So as we go up in the atmosphere, the pressure decreases. And that means if we take this piece of air up, without an actual structure around it, it has to match the pressure around it at all times. So if we take this up further in the atmosphere, its pressure will decrease. If we take it down, the pressure on this will increase. So we take this parcel, we raise it up, and it expands a little because the pressure on it is smaller. Right? And when we decrease the pressure on a parcel of air and it expands, it also cools down. The same way if you have a gas bottle running your barbecue and you run it for a while, that gas bottle gets cold. If it's really cold, it might form ice on the outside. So as the air expands, it cools down. And this is the reason why we have a pretty aggressive cooling in the lower layer of the atmosphere. Because when you have a thermal, it's lifting all this air up, it cools down, and it mixes everything to be about that temperature. So we go up, it cools down about 5.5 degrees Fahrenheit, 1,000 feet. Okay? And so go back to our notes here real quick. And then the reverse happens if we were to displace this parcel downward. So if I take my parcel of air, take it downward, now the parcel is going to compress down, it's going to get smaller. As we compress it, it's going to heat up. So like you have your air compressor running in your shop, the tank of the air compressor gets warm because you're heating up all this air as you're smashing it into the tank. So let's imagine for a second, thinking about the stability of a parcel of air. Take my eraser. I've got one here. I had to steal some after you cleaned up coffee with my first set of erasers. So, take our parcel of air and we raise it up so that it's cooler. All right? So it's bigger and it's cooler. And if we're thinking about whether it's stable, we're asking the question, what does it do now? So if the environment around that parcel of air has cooled off more than the air has, that is, we're back to this diagram that I just erased. So let's say we take our parcel up and the parcel cools off only like this. Everyone see those two lines, hopefully? Again, we have temperature and altitude. So the parcel is still warmer than the air around it. And if the air is warmer, this is like a hot air balloon. It's an imaginary hot air balloon, okay? If the parcel is warmer than the air around it, it still has a force from being warmer and less dense, that keeps pushing it up. And it will continue going up. So here's our parcel, here's the environment, and there's that inversion we talked about. The parcel continues going up until at some point it's no longer warmer than the environment. And at that point we'd say it's now stable. Now let's imagine in a stable environment. When the temperature increases with height, we would call it stable. And the reason for that is, so here's my new parcel. So we said it was warmer than the environment, and we were going to raise it up. It very quickly, as it cools off 5.5 degrees per 1,000 feet, it very quickly becomes the same temperature as the environment. Does that make sense? Or we could imagine if we took some air in the environment. So here's my stable environment. If I take some air in the environment and raise it up, now it is immediately cooler than the air around it. And now this imaginary hot air balloon it's negatively buoyant, it's dense, it wants to descend. And so it's going to descend back down. Now, the key thing to making wave is that in the atmosphere away from the surface of the Earth, there's very, very little friction. So if I can get a piece of air going, it's not going to want to stop until it hits something or until it becomes so negatively buoyant or so buoyant that it stops moving. And this means that if I manage to displace a parcel of air, my imaginary balloon, away from the level that it wants to be, where it's the same temperature as all the air around it, it's going to, if I raise it up, now it's too cold, it goes down, and it reaches the level where it wants to be, but it's moving down. And it has a lot of inertia. Air seems pretty insubstantial, but if I were to get, let's say, even the air just around your glider weighs more than your glider. Right? Air is really relatively massive, and if I get that much air moving, it's not going to stop all of a sudden, and it'll overshoot. So let's imagine my parcel of air here. So I have somehow raised it up above the level it wants to be. So let's say here, when the air is at this level, it's the same temperature as its environment, and we're going to use temperature as a proxy for the density. So when the air is the same temperature as the environment, it's happy. It's going to stay right there. When it's cooler than the environment, it's going to sink. When it's warmer than the environment, it's going to rise. And somehow we moved some air up. It cooled off, and since we were in a stable environment, it cooled off less than the air around it. So now it's cold air, it wants to go down. And so let's imagine a second or a few seconds in the future. This air has now started moving down because it's cooler than the environment, and it got to where now it is right at the level it wants to be. Well, what's the problem here? Yeah, the air is still moving. It's moving downward, and it doesn't have anything to slow it down until it gets below this level, and it starts heating up. And so now it's down here. It finally went so low, it heated up enough that it got buoyant and stopped. But now it's going to go flinging back up again. And it's going to get back to the level it wants to be, but it's moving, and then it's going to go back up again until it stops. Now I drew all of these right next to each other for a reason, and that is if we imagine instead of an air, we could have a piece of air that just bounces up and down in the same place. But that's pretty boring. If we were to get some wind blowing this piece of air along, so that here it is, and then it moves a little ways as it goes, and then it moves a little further, and now we have a wave all of a sudden. And so the only thing we have left to do is figure out how we displace this air in the first place. But if we put a mountain here, that mountain's going to force the air to go up as it goes over the mountain, and we've kicked off a wave now. And so this is the reason we have a wave, because we have a stable environment where the air is trying to return to its level of equilibrium, but it gets moving and has trouble stopping moving. And it may go, if we're in the lee of the Rockies, it can go hundreds of miles before it gets enough friction to stop it. So this is why we have a wave, and I want to make one note before we go a whole lot further, and one is that there's a tendency when we try to think about waves, especially in the atmosphere, to try to draw really nice analogies to water waves, because we've all seen water waves, and they're nice and familiar waves, because waves are kind of weird to think about. the problem with water waves is that a water wave occurs, it's a surface wave. That is, it occurs at the interface between two different things. And that kind of wave is in many ways different than the waves we have in the atmosphere. In an atmosphere, you're not at the interface of two media, you're at the whole depth of the atmosphere. So you have a wave now in kilometers and kilometers and kilometers of liquid, whereas the wave in the surface of the water is only a few meters deep. It's not that deep a wave. So internal waves, those are the waves in the atmosphere that go through the whole body of a liquid or a fluid, are quite different than the waves you get on the surface. And so while we see phenomenon in water waves that are qualitatively, that is, they look kind of like waves we see in the atmosphere, I would encourage you to avoid trying to overstrain analogies between water waves and atmospheric waves. Because the movement through the depth of the atmosphere, which is what we want, is really hard to get in a water wave. So let's look at a schematic of a wave system. And while I'm going through this, by all means, at any time, stop me if I've radically run over something and I don't know, not explained it thoroughly. But yeah, it won't offend me if you stop me. So here we have the ground, and we have a mountain. And the air is coming up, it's displaced over the mountain, and it starts oscillating on the other side. All right, so there's a few things that we want to note in this system. One is that notice where the wave is, and more importantly, where it's not. The wave is not right over the mountain. The mountain is what kicks the wave into gear, but you're not going to find the wave immediately. This isn't the world's biggest ridge lift. It's not like you're in ridge lift and it just keeps going up to infinity. We call them lee waves because they occur in the lee of a mountain. And in fact, much of the disturbance that the mountain causes is almost entirely in the lee. There's relatively little interaction at the immediate in front of the mountain. The other thing is, you can imagine at the surface, the wave is going to have to follow the shape of the mountain. This is what eventually kicks it into gear. But there's a problem here, right? Nobody goes downwind of a mountain and finds itself in a vacuum. Otherwise, Colorado Springs would be a pretty inhospitable place to live. So what happens is the air doesn't really like this, and it tries to make something that looks kind of like a mountain there. It starts circulating around, and so you get a relatively turbulent region that we call the rotor. And so this is just the air's, it doesn't like there not being a mountain there when it wants to be going back up, and so you get a rotor there that makes the air look kind of like there's a mountain. And then the other thing we want to notice is it can continue potentially for some distance downstream. All right. So a few things that we want to note that could happen here in terms of other parts of a wave. If over here I'm going to draw my temperature diagram again. So here we said was the temperature, it gets kind of stable, and that lets us have a wave. The thing that I didn't draw before is the dew point. Right? So this is, if we cool air to the dew point, this is the temperature at which we start getting condensation. So the dew point frequently looks something like this. We have some spread at the surface. It generally kind of narrows in the well-mixed layer, and then it might go somewhere else. But let's say we have an environment, it's kind of dry in the lower levels, and then it gets kind of wet up here. There's a lot of water in the air. And so we have a point where the temperature and dew point are pretty close at altitude. They're maybe only a few degrees apart, maybe 5 or 10 degrees. Remember, as we move air up and down, it cools off by 5.5 degrees per 1,000 feet. And so let's say this air is going up, it cools off, and so there was relatively little spread here. It goes up a little ways, and maybe now, when I have this parcel of air going up and cooling off, right, it cools off about like that. We're at the dew point. What's going to happen now?
Cloud.
Exactly. So we're going to get a cloud that starts forming here. As it goes over the wave, the air starts going down. It's going to end up below the dew point. That cloud's going to start evaporating. And so we have a wave up there, or a cloud up there, sorry, excuse me. And so this is where our lenticular clouds come from. We have enough moisture somewhere in the wave that when we raise the air up, it reaches its dew point, starts condensing water, and then as it descends on the other side of the wave, it evaporates again, and then somewhere over here, it'll raise again, and we'll get another cloud. And we have the typical banded structure that we associate with wave all the time. And we have our lenticular clouds, and in between the lenticular clouds, we have our phone gaps. And so this is the reason why we get these. The other thing that I want you to notice, I've got it somewhat exaggerated here, but if you're flying your sailplane, you would expect to be able to climb from somewhere like here up to potentially well above the lenticular clouds, right? Notice how if we were to track a fluid particle, it doesn't go up and down very much. Our parcels are oscillating over fairly small amplitudes. And we're actually crossing over streams of air as we fly our sailplanes. We're not going only as high as a single parcel of air. We're crossing over many of these streams and climbing much higher than any individual piece of air is going to go. Now, one note before we move on is when we're talking about the clouds, and especially in the Northeast, this can be a challenge. There's another way we could get clouds. We could imagine what would happen if, flying in the State College area, we have Lake Erie upstream. Maybe Lake Erie got to running. And instead of having to lift the air, if we injected some more water upstream, we could have, all of a sudden, the dew point moves up and becomes coincident with the temperature profile everywhere. And at this point, even if I'm moving the air up and down, it's going to stay totally wet, stay condensed. And this is the case where you could be up here above the lenticular clouds, and it doesn't, if this is only a few degrees, you could get that much moisture move in on you. And this is the case where you can have a wave window slam shut underneath you and you find yourself stuck on top. The wave is still working because it's kicked off by the mountains and the wind, but it just takes a little increase in the dew point profile, and you can saturate the whole wave. One more thing that I want to note, because it's going to introduce the next point here, is...
I have a question.
Yeah.
So what kind of clouds would they be, which are shutting?
It's going to look like a stratus-stack. It's going to be a lenticular cloud. You're forming it from orographic motion. Wave clouds in the Northeast you don't get like the classic perfectly laminar wave clouds always, like you would in Tehachapi or somewhere. So sometimes they do have something of a convective look to them, but they're stratus-y looking clouds, or sometimes trending towards lenticular looking clouds. But it's going to be a consequence of just getting more moisture in upstream.
Are those clouds stationary, or are they moving with the wind?
The lenticular clouds, or the
Lenticular, actually, when you overcloud entire area.
So the lenticular clouds are stationary with respect to the wind. This wave structure is stationary, and the lenticular cloud is formed by raising that parcel above its dew point altitude, and then as it descends on the other side, it dries out. So this cloud it's stationary with the wind, by which I mean it's constantly forming on the upwind side and constantly dissipating on the downwind side. And if you go out on a really good wave day and just stop and look at these clouds, it's sometimes really spectacular because you can see it happening. And sometimes you might get a slightly moister thing in front of the cloud, so you get a tendril that starts condensing ahead of the rest of it, and you can see it get swept up into the cloud, and then you can see things. You've all seen this in cumulus clouds. You can see them dissipating on the downwind side. It's sometimes very spectacular.
But the clouds which are shutting the phone gap are also stationary.
Yeah, they're
in a sense.
stationary. So what you would expect to see as the moisture increases is the cloud starts forming earlier and starts dissipating later. And so when we say slamming shut, if we imagine, I'm going to draw another little diagram here. So here is my first wave cloud, here's the phone gap, here's my second wave cloud. So this cloud starts lasting longer, this one starts forming sooner, and when we say slamming shut, it's because the clouds start meeting. And you look down and it looks like, you know, a set of gates, I don't know, like something out of a bad science fiction movie, you know, flying between the closing doors. Yeah.
Because we generally fly thermals, we think that the cloud base is the limit of the lift.
Yeah.
I see you did say that the dew point, it looks like it's the top of the wave level, but the wave will go higher than the dew point.
Yeah, so we can keep this wave. This wave will keep going as long as the conditions for it are appropriate, which are totally separate to first order from the conditions necessary to make a cloud. Yeah.
One thing I always wondered is why does the wave actually go so much higher than the trigger? What's the motivation of the air to go that higher? I mean, you explained with the bouncing ball and they displaced it up, and it goes up and down. Where's the energy coming from?
So the energy is coming from, I mean, you've got to force the whole atmosphere over the mountain.
Yeah.
And the whole atmosphere is somewhat upset about that. And there's, I don't have a
momentum, right?
yeah, and you have the wave, it has to keep up with the mountain. And so in effect, the wave and the mountain are, you can think of it, instead of the wind blowing over it, they're running along together. And you have conditions where the wave can't keep up and then all the energy goes downstream. But if the wave can keep up, the energy's got to go somewhere and so it gets shot up. I don't have a really brilliant, like,
But
you know, not
I mean,
Richard Feynman,
the
unfortunately.
lenticular
but-
cloud forms
Yeah.
because that air is going higher than it was upstream of the mountain.
This air, it will end up oscillating about the same level that it was before.
Right.
So the air is not displaced upward on average. But this is what I was saying, you're not tracking one fluid particle, you're having to
Right.
cross streams of fluid particles. And so the energy that is put in by forcing the whole atmosphere over the mountain ends up in a bunch of different streams that you're able to climb across.
So is it not parcel upon parcel just stacked up being shoved upwards?
So you have, you know, parcel 1 and parcel 2 that are disturbed, and you will cross over from parcel 1 to parcel 2 to parcel 3, etc.
I mean, in terms of it going higher, is it parcel upon parcel upon parcel that's actually?
Is it basically because there's no vertical compression? Is that why that's why the energy gets carried up?
So why does it have the same motivation on the left side of the picture? That's always what I don't understand. Why is it? I mean, okay, you can say okay, the air is going up and everything above it is going up as well. Why does that not happen on the mountain as well?
Yeah, are the parcels all the same depth as it goes over itself?
Sorry.
Are the parcels all the same depth as they go?
So parcels, you can draw your lines around your parcel however you want. There's not a standard parcel. So I've drawn them all the same depth, but I mean, in between here, there's an infinite number of them. Unfortunately, well, so as to your, hopefully if I answer your question, this one will be a little clearer. When the wave is trying to outrun the mountain, that is the speed that the wave wants to go. You imagine, again, if we were to hold the wind still, we could get the same picture by having the wave and the mountain run along through still air, if that makes sense. And if the wave wants to go faster than the mountain, you know, it can't end up over on the other side of the mountain. And so all of the energy that the mountain is putting into the wave gets stacked up when the wave tries to outrun the mountain. Because you have, let's say it's been running for 6 hours, you have all that energy, and that energy is constantly trying to propagate further forward and get over the mountain. Let's imagine this case where, you know, in a perfect world, we would actually just have one single wave on the other side of the mountain, and not any, you wouldn't have a secondary or tertiary or anything. We had a perfectly vertically propagating wave. The speed of this wave is potentially faster than the speed of the wind. Okay? And that doesn't make any sense because if the wave ends up on the other side of the mountain, there's no trigger. And so what it does is it starts leaning over. So the next wave looks like this, and the next wave looks like this. And the energy that would have ended up down here has tried to run forward and stacked up. And so this is the reason why you can get to high altitudes. You're not looking at the energy of one fluid particle going over the mountain and running off to the Atlantic Ocean. That energy is able to make it back upstream and is trying to get over the mountain, and the only thing it can do is make the wave stronger because it can't get over it.
So how does this explain the wave triggered by the drop of the plateau?
The drop is you have to start that oscillation. These particles are perfectly happy running along right in concert. And so if you don't get them oscillating, you can't have a wave that tries to run upwind. I can see that was a wonderful Yeah.
Does the inversion have to be below the mountain top?
I'm going to get to the inversion in a second. How's that? Yeah.
What effect does wind gradient? Does that add energy to the
That's the next topic.
Okay.
Right.
A follow-up question.
Yeah.
How do you get stacked linees? Sometimes you'll see linees.
Yeah, so
stacked.
if we have multiple places where the temperature and dew point is close, actually I should have drawn, so the temperature, let's say, goes something like this. If the dew point gets kind of close, and then we have several places where the temperature and dew point is close, we can have gaps in between the
So
clouds.
like moisture at different levels, maybe?
Yeah, exactly.
Is that also,
Go ahead.
is that also why you can also get rotor clouds and then linees, or?
Yeah, or you may be able to even inject moisture at the surface down where the rotor's floating. But
Compression and expansion of the particles themselves, what's taking place there?
and can you clarify what you mean?
Yeah, I guess as you're coming over, I
Yeah.
think as it's stacking up, of course, it's pushing on each other, and you've got compression of those parcels. Right?
Yeah, so
And then as it frees up, now they're expanding, I would think, but
so as they go up and down, they're matching to kind of a reasonably close approximation, you could say, but they're going to have the same pressure that they would at that point in the atmosphere, right? As the pressure drops off as we go up in the atmosphere. And it's going to be, the wave is not going to dramatically affect the pressure level in the atmosphere. So if we raise a parcel up, it gets lower in pressure, it expands, and we sink
so
it.
hitting the disturbance of the mountain, let's just say, or that area of the mountain, as it's going over and pushing that stack up, it's not compressing in any way.
It will largely not compress it any more than it will simply by displacing it. So I think he had a question. I was trying to
In your diagram, it
Yep.
shows how the mountain acts as a trigger for the wave.
Yep.
If you had, assuming everything else is the same, but instead of the mountain there, you would have a plateau to the left.
Yep.
How would that affect the wave in that picture?
It doesn't dramatically affect the overall picture. What you need is some way to displace the air vertically, and that's, so this is the reason why you can get waves over thermal streets or waves over all kinds of things. If you get the air displaced so that you start this oscillation, and the point that I'm going to make in a little bit is that once you start the oscillation, the mountain has more or less done its job. The mountain has less impact on the overall wave structure than it seems like it should.
Okay. But my question is, in the case of the mountain,
Yep.
you can imagine that right before the peak of the mountain, you have, just like ridge lift, you have air actually going up
Sure.
and then coming down. If you had a plateau there, if you just imagine
Sure.
from the
Thinking
peak,
like
a flat line all the way to the
that.
left, you wouldn't have that effect. All you would have is the drop. So my question is, how would, looking at the cap area and the area beyond it, would it be a big effect on that wave or a minor effect?
It would affect it in the region of the cap, but the wave following would be
Always the same?
relatively
Would it be
unaffected.
virtually the same?
It
So
would
it
be
would be
very
just the
similar.
cap that would be affected?
Yeah. Yeah.
On the upwind side of the mountain, are you getting any heating due to compression?
I mean, as Dr. Malmer likes to say with these kinds of questions, when you pee in the ocean, does the level go up? So it will heat up to the sense that, so actually in some sense the air going up the mountain cools down, right? Its pressure decreases because it moves vertically in the atmosphere. And the vertical pressure gradient is what dominates the pressure changes with it. I mean, you can get pressure oscillations in the wave, but those are deeper than the kind of wave theory that you need in order to fly a glider in the wave. Yeah.
I have two questions.
Yep.
You started off by saying that there's an inversion that develops.
Yeah.
I don't understand why you have the inversion. And the second question is, as the air comes down, the downside of the wave,
Yep.
wouldn't it accelerate and then decelerate on the upside, causing a bunching up in between in the valley?
It does, but that effect is less interesting to us than the fact that it's going up and down. It's harder to, it would be harder to soar on something that's accelerating and decelerating. But,
For the first question, please.
Oh,
The inversion.
sorry, what was the first
I
one?
don't, okay, we have.
Oh, the inversion.
We started off by talking about inversion developing. I don't
Phil
understand
will probably
why.
talk a little
Yeah,
bit
we'll
more
talk
about the
inversion.
formation of this inversion. The kind of longer answer is that when you get away from the surface, most of the depth of the troposphere is what we would, in a meteorological sense, call inverted. It may not actually be getting warmer with altitude, but it is getting warmer with altitude, or sorry, it is getting cooler with altitude at a rate that is different than the parcel would be. And that is, in a meteorological sense, inverted. That is that it is a stable profile where when I raise a parcel of air, it will now be cooler than the environment around it, which is what I mean by inverted.
It's not actually physically getting hotter.
Yes, it's almost, well,
It can.
right above the
It
boundary
can.
layer, it can physically get hotter, but most of the depth of the troposphere will not get hotter.
Yeah, I have a question regarding the mechanism of it. So you're saying that the elasticity of the whole air mass has no factor in the moving of the wave? It's just the temperatures?
What do
In
you
other
mean by
words, the
elasticity?
compressibility, like a spring factor, would that add to the wave or not have an effect at all?
So it is rather difficult to get really significant pressure differences that are non-hydrostatic, that is not due to the pressure changes because you have more or less air above you. You can get pressure differences like that, but they're relatively small. If you want to really predict the structure of a wave, you have to consider them, but to understand wave well enough to fly a sailplane in them, you can ignore all of that.
Are there conditions where a second row of mountains can magnify the effect of the wave?
Yes. So there's, if we're going to mix meteorology and aerospace engineering a little bit here, we often say, when you're talking about fluid flows in aerospace, that you can replace any stream of air by a surface and the air won't care, okay? And so we could replace this by a mountain and the air doesn't care. And so we could draw a second mountain in and we would change, it would be like if you had now, let's say this oscillation is relatively small, but if I put a big mountain in, the air's got to go over it, and so we could this looks like the wave is enhanced right here, and the rest of the wave has to follow.
Do those like affect the flying that you guys are able to predictably do from time to time?
Yes, absolutely. Especially if you can have a long range of them that are reinforcing. So this is, if you want to fly in central Pennsylvania, that may be a good place to find these kinds of things.
Ask that question again, my shot.
Yeah.
I'll get that.
Yes, I would like to go back to your explanation of this effect. So you say, on one hand, we have the energy doesn't want to go to the other side of the mountain, and because of that, the whole thing is getting
Stacked up. Yeah.
right. So now, on the other hand, we also have those secondary and tertiary
Yep.
waves. Aren't those two effects sort of, say,
This is the next section.
contradictory to each other? I'm sorry.
Yeah, no, that's okay. It's a great question. So you and the people wondering about what happens in the wind profile, what happens when we change the temperature profile, this is the next section. I want to get the basics here clear before we move on. Yeah.
Is wave entirely contingent on wind, or is it possible to have wave without wind?
So in principle, if you were able to just place a parcel of air up in a stable environment, it will sit there and oscillate, and you could fly in wave for a while, and then it will be sink, and then it will be wave, and then it will be sink. You know, when we derive how fast it goes up and down, that physical principle doesn't care whether it's moving or not.
But it would dissipate, so you'd have to redo it.
It
You'd be
will, but
losing energy.
it'll take a while. There's not a lot of friction in the free atmosphere.
So if you took one parcel
Yep.
like that and let it drop, I mean, imagine an imaginary experiment. You don't think it would like stop very
It
soon?
would, but it'll take a little while. It would probably make a couple oscillations before it stopped.
Yeah, a couple makes sense.
So some of those thermals are the second oscillation?
No, because thermals are in an environment where you can't have an oscillation. It is unstable, so that when that thermal gets going, it doesn't want to stop until it hits the inversion. But sometimes it'll overshoot into the inversion, and then it comes down, and that's sort of an oscillation. But, all right.
Sorry.
Okay, Daniel's telling me I need to move on, so, sorry. So the next thing that we may do is somewhat briefly in order to give Phil some time. But, so this question of what happens when we change the wind profile, what happens when we change the temperature profile, what happens to tertiary waves or secondary waves, and when can I climb really high, turn out all be kind of the same question, okay? And that is, one point I want to make first is when we were talking about the wave, how we set up a wave, we talked about the air oscillating up and down and the wind blowing that oscillation along. There's relatively little mention, almost no mention of the mountain in here. The mountain's job is to get the oscillation started. Once it does, that oscillation depends on the stability of the air and how fast it blows along. The mountain's job is done once it kicks the wave off. And so we can imagine we had a really stable layer. So the temperature's increasing fairly rapidly with height. Right? In this layer, if we displace the air up, it's strongly negatively buoyant. If we displace it down, it's strongly buoyant. It's going to oscillate very fast. Okay? If we have a layer that's less stable, we raise it up and it kind of wants to come down, but it's not really in a hurry to do it. And if we sink the air down, it kind of wants to come up, but it's really not in a hurry. So we get longer waves. All right? So now, what happens if we have this? Right? So we have a really short wavelength wave that is trying to get up into a layer that wants a longer wavelength. Okay? And to explain what's going to happen, my lab recently acquired a general purpose oscillation demonstration unit that I was able to borrow. So here we have it, okay? And if I have a short wavelength that's trying to get into a layer that wants a longer wavelength, what happens? The bottom of the slinky doesn't move very much, okay? If I go the other way, if I have a long wavelength trying to get into an area that wants a shorter wavelength, even when I'm forcing it at a much lower frequency than it wants, we get a large deflection of the system. So we can go from a long wavelength to a shorter wavelength, but going from a shorter wavelength to a longer wavelength is a problem. And so when this happens, the wave is able to make it kind of up here, but this starts damping it out. And this is the case where we have a wave, so I'm not going to draw the mountain because the mountain's done its job. We have a wave, and up here is where it gets into that environment that wants the longer wavelength. And since the air up there wants it to oscillate slower, it cannot support the oscillation at this frequency. Just like you saw when I tried to shake the slinky too fast, it would die out by the time it got to the bottom of the slinky. And so this wave just sort of slowly peters out.
One clarification maybe.
Yeah.
You didn't mention, I think, that the natural wavelength has to do with the wind speed, right?
Yeah, there's a natural frequency of oscillation that's dependent on the temperature profile. And for that, the air goes up and down and takes so long to go up and down, and how far the wind blows it in that time makes the wavelength, right? Because it's going to take some unit time to go up and down, and then the wind will blow it that far. So if the wind blows it twice as far in that time, we have twice.
So that would be one of them, and the other one that would be conflicting potentially would be the lapse rate, etc.
Yeah, you're getting a little ahead of.
Right. But you mentioned there are two and they're conflicting. You didn't mention what the two were, so, right? Because you said one is the one that has to do with the
right now
inversion.
I'm just talking about temperature differences.
Right.
The temperature differences can give rise to, this is assuming we have constant wind. We'll introduce the wind in a second.
Okay.
And so when we have the wavelength suddenly grow, the wave is slowly going to die out. And so when we talk about trapped waves, right, and since the energy can't get upstream anymore, now it's going to end up going downstream, and this is when we get long runs of trapped waves. where you can have tertiary and quaternary, and in Kansas sometimes they would get wave that would shut up off the Rockies and manage to make it all the way out there. And this hurt my head a lot when I was trying to figure this out at first, because I'd always associated really strong inversions with trapped waves. And the figuring there was, okay, the inversion is what's stopping the wave. And the problem is not the inversion stopping the wave, the problem is when we get to the top of the inversion, now the wave can't make the jump from the short to the long wavelength. And as he's trying to get at, the other way we could do this, let's say we had the same inversion the whole way up, or the same temperature profile. But halfway up, so if we look at the wind, so we have some wind, and halfway up, we double the wind. All right? In the same amount of time for that same oscillation, the parcels are going to go much further. And so we lengthen the wavelength. So we can trap a wave using both temperature structure or using the wind structure. Does that make sense? Good. And so I'm going to try to wrap up here pretty soon, but the point that I want to make with this is that when we want to get deep wave, we want to get a relatively moderate low-level inversion. If we make that low-level inversion too strong, it's a hard jump from that inversion to the temperature structure above. We want wind and temperature to change relatively smoothly with height. But overall, there is this complex interplay that he's trying to get at. And this is what can make wave forecasting really challenging. Phil's going to talk about this a bit more. Because when I go look at flying thermals, I look at a sounding, the temperature and wind versus height, and I can say, this is a good day, or this is not a good day. When I look at that sounding, when I'm thinking about wave, there's not, we don't have the clear boundary layer that says, this is a good place to fly thermals. You don't get that for wave. Right off the sounding, there's nothing that jumps out at you saying, this is the wave area. Because that temperature structure that looks really wonky, it might be fixed by a weird wonky wind structure. Or you might have a great looking wind structure and the temperature structure might ruin it. And this can make wave forecasting challenging.
Those are predictable, more or less.
They are predictable, but they take a little deeper dive into the atmospheric structure.
I would imagine you end up, if you're trying to predict, you have to look at the reinforcing geographic contours as well as far as wavelength and things of that sort.
Yeah, if you're looking, if you want to get the reinforcement, you can get pretty good waves off of the single structure.
Right.
But if you're interested in the reinforcing things, you need to look at the wavelength to make sure, if it falls out of phase, you can wreck the wave with it.
That's really what I'm trying to do.
Yep. Or if you're flying ridge and you got a wave coming at you, you can wreck the ridge. Yeah.
Yeah, for sure.
Yeah, coming back, so I didn't catch one thing. So in what situations the energy cannot go to the right, and in what situation it does produce?
Okay, so these situations, if you were to go work out the equations on these situations, these where we have the wave trapped, that is where the wave is no longer propagating fast enough to keep up with the wind. And this is why we get trapped lee waves that go way downwind, because they can't keep up and so they blow downwind. And they take all of the energy that would make a nice big vertical wave that we could climb in, and they suck all that energy out downwind, out to the Atlantic Ocean, or to Kansas, or to wherever. Whereas if all that air can keep up, if all of a sudden we were able to get 3 days worth of air that was getting blown downwind, or 3 days worth of energy, and it was going fast enough to keep up with the mountain, you can imagine now it piles up and we can go climb and get our down goal.
So it's accumulation of this energy in time, that's what's happening?
That would be one way to think of it. So, all right. You want me to get to Phil now? Sure. All right. Thanks. I'll be around, so.